All right, in this video here, we're going to talk about what we call the natural exponential function, which is the exponential function with base e. Right now, if you haven't seen the other videos that I did on the number e itself and an explanation of where that number comes from and what it's equal to, you should definitely check that video out. Also, the videos that I did about just exponential functions in general and what their graphs look like, you should really check those out before you watch this one, because I'm going to use a lot of the information I talked about in those videos to explain what's going on here. Right, so the natural exponential function is the function f of x equals e to the x power. Right, and sometimes we just call it the exponential function. Right, this function comes up a lot when we are dealing with real life situations, when we're trying to model real life situations like population growth or compound interest or the decay of radioactive substances. There's something called Newton's law of cooling, where you put a hot cup of coffee in a room temperature, and how quickly the coffee cools off is based on this exponential function with a base of e. Right. So now, if you watch the other video I did on e is approximately 2.718. That's the approximate value of e. It's an irrational number, but that gives us a good approximation of what e is equal to. So that number as the base comes up a lot in these real life situations because of a special feature of the graph of this particular exponential function, which I'll explain to you here. Right, so here's the graph of f of x equals e to the x power. Right, if you watch the video that I did on the graphs of exponential functions, it looks like just like the graph of any other exponential function whose base is bigger than 1. Right, so if you go back and look at that video I did on the graphs of exponential functions, I had the graph of 2 to the x power and also 3 to the x power. Well, since e is 2.72, it's in between those two, the graph of e to the x is right in between the graph of 2 to the x and 3 to the x. Right? It's very similar to the graphs of all those other exponential functions. Right? But there is one feature of the graph of this exponential function e to the x, and it's the only function that's like this, which is why this one is so important, or one of the peculiarities of this function, which makes it so important and why we use it to model so many real-life situations. Right, and what that peculiarity is, which that's a hard word to say, what that thing is about this function is that if you go to any point along the graph of f of x equals e to the x, right, so take this point here, which has some x and y coordinate, I'll just call it x comma y, right, at that point, if I take the slope of the tangent line at that point, now what a tangent line is a line that just barely touches the curve at that point, right, so it kind of like goes along, and at that point it just barely glances off the curve, and then it goes on its way. Right, but the slope of that tangent line is equal to the y-coordinate of that point on the graph. Right, and that's true of any point along the graph of the function f of x equals e to the x. If I draw the tangent line and find the slope of that tangent line, it's always going to be equal to the y-coordinate of that point on the graph. Right, which, like I said, is the only function out there that has that that thing about it, that fact. Right, where the slope of the tangent line is equal to the y-coordinate. Now, why that's important as far as modeling real-life situations? Well, remember the slope, and if you've seen some of the other videos that I talked about linear functions of slope is the rate of change, right? And the slope of a tangent line to a curve at a certain point. This is kind of a topic that you get into in calculus, and in a Calculus 1 class, you'll kind of get a deeper explanation of all this. But at that point on the graph, the slope of the tangent line, that's the rate of change of that function at that point. So what this is saying is that at this point here, the rate of change of the function is equal to the value of the function, the y. Right? So the rate that it's changing is equal to the amount or the value that it has at that point. Think about it in terms of like a population growing. Let's say you have a population of giraffes. I don't know why I thought of giraffes, it just popped into my head. All right, so if I have a population of, let's say, 6 giraffes living together somewhere, right, they're going to reproduce and they're going to create more giraffes, but their population is going to grow slowly because there's only 6 of them that can reproduce and have baby giraffes, right? So the lower number I have, the more slowly, the less steep the population curve is going to increase because there's so few of them creating more, right? Whereas if I had a population of, let's say, 100 giraffes, right, so like I have a much higher value now. Well, there's a lot more ways that those giraffes can reproduce and create more babies. So their population is going to grow more quickly than the population of only 6 giraffes. Right, the more you have, the more you have there at the time, the more quickly it's going to grow. Right, the faster the rate of change, or the more steep the curve is going to be. Well, the amount present is like the y value, right? The slope is like the rate of change. So the bigger the y value, the bigger the slope is going to be. Well, for this exponential function, the y value equals the slope, right? So the amount present is proportional to the rate of change, which is why we use this exponential function e to the x to model things like population growth, or think about it in terms of compound interest in your bank. The more money you have in the bank, the quicker it grows because it's calculating interest on a bigger amount. If you only have $1 in the bank, you're only going to earn like a cent or two of interest each month, whereas if you have $1 million in the bank, you're going to earn a lot more interest each month, and your money is going to increase at a quicker rate. Right? The more you have present, the bigger the y value, the faster it increases, the bigger the slope. Here, since the slope equals the y, right, the rate of change equals the amount present, that's why we use this exponential function to model so many real-life situations, right? So that's one of the main reasons why this exponential function is so important, and why we call it the exponential function. E to the x is a very special function, and you'll see more of that, like I said, when you get into a calculus class. You'll learn a little bit more about the exponential function and see some other reasons why it's so important. All right, but that's what the graph of the exponential function looks like, that one feature of the graph, which is why we use it so often. All right, what I'm going to do now is pause the recording and erase this stuff, and then I'm going to put up some example problems where we work with the exponential function e to the x. All right, so here we have some examples of basically just evaluating the exponential function of e raised to a power. And I didn't mention this when I had the graph up there, but just like for the graph of any exponential function, the domain is all real numbers. So I can plug in any number for x and raise e to that power, and it's going to give me a result. And the range is just positive y values. So when I plug those numbers in for x, the result is always going to give me a positive number when I just have the function f of x equals e to the x. All right, now when you're evaluating functions that involve e, right, this particular exponential function, even if you have nice exponents like a 3, since the base e is an irrational number, in order to do this calculation, you're going to use a calculator for it, right? Any scientific calculator, any graphing calculator has an e button on there. It has that value of e stored in it, so you can use what's stored in the calculator. Like, you don't have to memorize that e is equal to 2.71828 and so on. You can just use the buttons on the calculator to calculate the e raised to all the different powers. All right, so on my calculator, which is a TI-84 calculator, and the TI-83 is the same way if you have that type of calculator. I showed you on another video where the e button is just e itself, which is above that division key. If you see in blue, it says e up there. There's also a button for e to a power, which if you look over here on the left side of the calculator, next to that 4 button, there's a button that says ln, and above that it says e to a power. Right, it's the e to the x button. Right, so if I want to raise e to a power, I'm going to use that e to the x button. So I would do second ln, and that brings up e to a power, and then I just type my exponent, which is 3, and I don't even have to close the parentheses if I want to be lazy about it, and it gives me the value of e to the 3rd power, which is 20.085536. I'm looking at the instructions here. Oh, we're asked to round these to 5 decimal places this time. All right, so if I round e to the 3rd power to 5 decimal places, I get 20.0855. So that's 4 decimal places, and then I have 3 6. So that's 6 next to the 3 tells me to round it up to a 4. Right, so just to show you what the whole answer looks like. So if I round that to 5 decimal places, that's the value of e to the 3rd power. Right, to do 2e to the negative 0.53 power, I type 2, and then I hit that second ln again to get that e to the power. And again, on your calculator, you might have that e button in a different spot. But if you have a scientific calculator, it's on there somewhere, so you just have to look for it. Right? So I have 2e to the power negative 0.53, hit enter, and I get my answer, which is 1.1 something. Right? So I get 1.177, that's 3 decimal places, 2, and then I have 0.9. So since I'm rounding to 5 decimal places and I have a 0.9 there, I round that 0 up to a 1 since it has that 9 next to it. Right? Remember, when you're rounding, if the number next to that 5th place is a 5 or higher, you round that number up to the next biggest one. All right, the last one there, e to the 4.8 power. So same deal. I mean, once you know where the e button is on your calculator, doing a problem like this is not hard. You're just typing it in, e to the 4.8 power, writing down your answer. Just make sure you round it appropriately. So this one is 121.5104, and then I have 1.7. So since there's a 7 next to the 1, I round that up to a 2. Right? So There's the answer I got on that one. All right, so that's an example of just evaluating the exponential function, plugging some different numbers in for the exponent of e. And I think the purpose of doing an example like that is to just make sure you know where that e button is on your calculator. Like I said, for any of these types of problems, you're going to want to use a calculator to do it. It's not the kind of thing you're going to be able to calculate by hand, since that base number e is an irrational number. All right, so just make sure you know where that button is on your calculator, because for a lot of work that you do with exponential functions and with logarithms that are coming up soon, you use that E button a lot, right? So a lot of the stuff we do with these types of functions involves working with the calculator. It's important to know where the buttons are and how to use them, which is kind of the purpose of doing this example here. All right, I'm going to pause this again and then put up another example that we'll take a look at involving the exponential function. All right, so in this example here, we got a word problem that involves the exponential function. All right, so we have an infectious disease that's spreading in a small city of population 10,000. After t days, the number of people infected is modeled by this function. V of t equals 10,000 over 5 plus 1,245 e to the negative 0.97t. And we're asked how many people are infected initially, how many after 1, 2, and 5 days, and then we're asked to draw a graph of this function and see what it looks like. All right, so to see how many are, since it's asking us how many are infected initially, remember, initially means at the beginning, which means t is equal to 0. Right, so basically I have to plug into this function t equals 0, and then for part b I have to plug in also 1, 2, and 5, and then I'm also going to have to graph this function. So since I have to do all that stuff, and again, since there's this e to the power here, I'm going to use the calculator to evaluate this. I'm not just going to plug in 0, 1, 2, and 5 by hand here and do the calculations. So what I did is I typed the function in the calculator. I'm going to show you how a shortcut, if you need to evaluate a function multiple times, like here we have to plug 4 different numbers into this function, rather than typing it in 4 different times with different numbers. If you just plug the function into your calculator, which, one thing about that, notice how when I typed it, I put the 10,000 divided by, and then I put the entire denominator in parentheses. Right? When you're typing a function like this to graph on your calculator, or even if you're just typing it on the main screen to do calculations, you have to make sure you put the entire denominator in parentheses, because remember, your calculator follows the order of operations. You need to make it do all this stuff in the denominator first and kind of add all that together before it divides the 10,000 divided by that whole chunk of stuff. Right? If you don't put parentheses there, it's just going to do 10,000 divided by 5, get that answer, and then add all this other stuff to it. And it's a real common mistake people make on a problem like this, is not putting parentheses around that denominator. Right, so notice the whole denominator has parentheses, and also the exponent on the e, right, that e to the power negative 0.97x, that negative 0.97x, that itself is also in its own set of parentheses. Again, because I need to make sure the calculator does all that stuff together before it raises e to that power. Right, so when you're typing complicated functions like this in your calculator, using those grouping things are important. Right, so if I type all that stuff in there, and then I hit second graph, right? If you notice above graph, it says table. So if you hit second graph, it gives me a table of values. Now my calculator is set up starting at 8. Now depending on if you ever used this before, usually it's starting at 0, but if you've used it before, it might be starting somewhere else. So I can just hit that arrow to scroll up, and it tells me when x equals 0, y equals 8. When x equals 1, y is equal to 20.966, and so on. So it has, the x values are all my inputs. So like if I plug in x equals 0 or t equals 0, I'm going to get 8. If I plug in t equals 1, I'm going to get 20.966. It gives me all the input and output values right there on that table. I don't have to type this in 4 different times and plug in 4 different numbers. I just type it in once on that y equals screen to graph it, and then I use the table and it gives me all those values. All right, so there's all my answers. So affected initially on when x equals 0 is 8. When x equals 1 is 20.96, which, since we're dealing with people infected, we're going to round it to a whole number of 21. 2 days is 54. 5 days would be 678. All right, so we can see how quickly that thing is growing over the first few days, just from that table of values there. All right, and then to graph it, well then, I already typed it in, so I just have to hit the graph button, and now it's going to give me a weird looking graph. So I'm going to pause the recording here and kind of fix the window so I can see the graph better, and then I'll bring it back and kind of show you what that graph looks like. All right, so here I set my window, my x between 0 and 15, my y between 0 and 2000, and when I graph it, you see the graph curves upward like an exponential function. In the beginning it behaves like an exponential function, but then it levels off and reaches like a maximum, like a plateau value, which is the most number of people that could possibly be infected. Right, this is called a logistic function. Having that exponential function in the denominator kind of forces it to level off like that. So that's what we got.